here we have two conductors and a voltage source attached to them, and we want to find the electric field intensity and the electric potential field everywhere. We have used a variety of techniques to find the electric field intensity. One of them was from Coulomb's law. So if we have some differential charge element, such as a rho sub s ds here from a surface charge, the contribution of the electric field intensity at some point is that charge, rho sub s ds, divided by 4 pi epsilon sub 0 times the distance squared from that differential charge to the point we're trying to find the electric field intensity, times a unit vector pointing from the charge differential to the point where we want to find the electric field intensity. Then the total electric field intensity is just the integration of the contributions to the electric field intensity from all the charge along the two plates. But we don't know the charge density on our two plates, so we can't use this technique. We also used Gauss's law to find the electric field intensity, but Gauss's law also requires knowledge about the charge distribution, plus we have to be able to match a Gaussian surface to the symmetry of the field, which again we can't do for this situation. A third way we could find the electric field intensity is by taking minus the gradient of the electric potential field, but we don't know the electric potential field. Now, actually contained in Gauss's law, actually the point form of Gauss's law, and E equals minus the gradient of the potential, is how we're going to be able to determine the electric field intensity and the electric potential field when we have two conductors and we know the potential of each of the conductors. Here we have the point form of Gauss's law, and here the relationship between the electric flux density field and the electric field intensity using the absolute permittivity. So we're going to substitute for the electric flux density field in Gauss's law epsilon times the electric field intensity. To proceed, we have to make one assumption, and that assumption is that the absolute permittivity is not a function of position. In other words, the permittivity is a constant. Let's see what that means for us. So let's see how we can modify this equation if epsilon is not a function of position. First, our del operator in Cartesian coordinates looks like this, and it's going to be dotted with epsilon times the electric field intensity, and here we have the electric field intensity written in terms of its three components. So taking the dot product, we'll have ax dot ax is 1, so we'll have a partial with respect to x of epsilon times e sub x, and then ax dot ay is 0, ax dot az is 0. Move to the second term, ay dot ax is 0, ay dot ay is 1, so we'll have a partial with respect to y of epsilon times the electric field component in the y direction, and finally the same thing for our third term. With epsilon not being a function of position, we can move it to the left of the partials with respect to x, y, and z, and now we can rewrite this as epsilon times the divergence of the electric field intensity. So the condition of epsilon not being a function of position means that we can move it to the left of our divergence and rewrite this equation as epsilon times del dot the electric field intensity is equal to the volume charge density. So epsilon not being a function of position means we can move it to the left of our divergent operation and then divide both sides of this equation by the absolute permittivity. Now for the electric field intensity, we're going to substitute minus the gradient of the potential field. And then multiply both sides of this equation by minus 1. Now this operation of taking the divergence of the gradient of a scalar field is written as del squared V. And this operation of del squared, which is the divergence of the gradient of a potential field, is called the Laplacian. So this equation right here, that the Laplacian of the electric potential is equal to minus the volume charge density over the absolute permittivity, is referred to as Poisson's equation. And in situations where there's no volume charge density, so that we can rewrite Poisson's equation as the Laplacian of the electric potential equals to 0, is called LaPlace's equation. Poisson's and Laplace's equations are second-order differential equations, and with knowing two boundary conditions, you can solve these equations for the electric potential field. Let's find the form of the Laplacian in Cartesian coordinates. So the Laplacian is the divergence of the gradient. So the divergence, we have the del operator in Cartesian coordinates, and we're going to take the dot product with the gradient of the potential, which is just the del operator times the potential. Okay, so this operation of the gradient gives us this form right here. And now when we take the dot product, ax dot ax is 1, so we'll have the partial with respect to x, or the partial of v with respect to x, which is just the second derivative of v with respect to x squared. Then ax dot ay is 0, ax dot az is 0. Second term, ay dot ax is 0, ay dot ay is 1. So again, we'll then have the second derivative of the potential with respect to y now. And ay dot az is 0. Third term, az dot ax is 0, az dot ay is 0, az dot az is 1. So we're left with the second derivative of the potential with respect to z. So the Laplacian in Cartesian coordinates is given by this expression right here. To get the form of the Laplacian in cylindrical and spherical coordinates, you just apply the forms of taking the divergence and gradient in cylindrical and spherical coordinates to get these expressions for the Laplacian in cylindrical coordinates and the Laplacian in spherical coordinates.